All right, so we're getting into power functions today, and really we're building our way up to polynomials. So we'll talk about power functions, and please remind me at the end, I do not have anything on your notes about monomials. There's information in the book, but if we have time at the end, I can give you some notes on what it is to be a monomial, because you will see that in your assignment. So let me kind of give you a preview of what we're going to do today. There's two kind of big parts for this lesson. The main part of it's going to be on the second page, and in this we are just going to review some stuff that we've already done. Back in chapter 1, we went through a big long checklist for analyzing functions. Do you guys remember all that stuff? X-intercepts, Y-intercepts, domain and range, increasing, decreasing, is it bounded, is it continuous, odd and even, all that fun stuff, end behavior. So we're just going to practice doing that stuff again, because that's something that we're going to do every time we get a new type of function. And then we're also going to practice doing some transformations by hand. By now that's probably going to be pretty easy for you. The new stuff has to do with power functions. I'll be honest, this stuff is not, it's not the most important thing that we're doing. Really, the second page is, but I do want to introduce you to the concept of a power function. And really, the big thing is, if you run into a sentence that describes a power function, can you use that sentence to write an equation? And then vice versa, if I give you an equation, could you use that equation to write a sentence? This is the type of stuff that's going to come up in like our science textbooks as you go on into your more advanced science courses. So let's just dive into it. This is a pretty short one. So a power function is always going to be in this form. K is what we call our constant of variation. And A is our power. And for power functions, both of those things are allowed to be any real number. They can be positive, they can be negative, they can be a fraction or a decimal, they can be an irrational value like the square root of 2 or pi, any real number. Do you guys know the shortcut for all real numbers, for the set of all real numbers? So I've got great news. Now that we're in chapter 2, you don't have to use interval notation for domain and range anymore. You can use shortcuts. This is the shortcut for all real numbers. It's a capital R, but it's got an extra bar on it. That is not an I. That is the double bar R. It's not IR. A lot of times my students think that's an IR, but it's a double bar R, and it stands for the real numbers. The real numbers are anything that doesn't involve I, basically. Were you guys aware of that thing? All right, so power can be a real number, and the constant of variation can be a real number, any real number. By the way, there's some other symbols. Do you know what the integers, do you know the symbol for the integers? This is another one that's going to pop up later this year. It's a double bar Z. That's the shortcut for the integers. Second semester we'll be using that when we're finding x-intercepts for trigonometric functions. All right, so let's just go through, we'll look at some equations, we'll identify the constant of variation and power, and then talk about the language that we would use to describe them. So all of these are going to have some basis in either geometry or science. Our first one is the area of a circle, it looks like to me. The power, we can tell that the power on this is 2, because that's the power. And the constant of variation is pi. If I wanted to describe this in words, if I were writing a textbook about the area of a circle, I might say something like the area is proportional to the square, or the area varies as the square of the radius. All right, so far nothing crazy difficult. Ooh, this next one's a little tricky though. What's the power on this? R is going to be our independent variable here. What is the power on R? It's not written, but you guys all know that there's an invisible 1 sitting there. So the power is 1. And the constant of variation would be, well, 2 pi. So if we're talking circumference, we would say circumference is proportional to the radius, or circumference varies as the radiance. Notice we didn't include anything about a square or a cube or anything here because the power was 1. All right. Okay, this next one's a little bit tricky too because it's not written in the form of a power function. I'm going to force it into that format. Let's review some exponent rules here. If I wanted to write this as k times d to a power, what power would be equivalent to having a d squared in the denominator? This would be a -2. Are we good with negative exponents and our exponent rules, hopefully? So this time around, our power is negative, and the constant of variation is just k. Now, whenever the power is negative, you're going to see this word inversely pop up in the language. So when we say force is inversely proportional to the square tells me that we're going to have a power of 2, and the inversely part tells me that that 2 is going to be negative. Okay. Questions so far? Does this seem too easy? Just right? Perfect. Just right. Let's keep going. All right, so here's a sentence that you might read in a science textbook or a geometry textbook. We're going to try and write an equation out of it. So the volume V of a circular cylinder, this is kind of bothering me. I feel like we don't need the word circular here, right? Is there any other type of cylinder? Let's get rid of that. The volume V of a cylinder with a fixed height is proportional to the square of its radius. So I'm reading this and I see proportional to the square. So what's that tell me my power is going to be on this thing? So the power is 2. And is it -2 or is it +2? +2, what word would be present if they wanted the power to be -2? But we don't see inversely here, so we're going to assume that it's to a power of +2. And then they're telling us what they want our constant of variation to be. So we just need to write an equation. They tell us V is the dependent variable, R is my independent variable. You guys figured out pretty quickly that my power was 2 and that my constant of variation was pi h. And that's it. All right. Last one here, speed p of a free-falling object. So I'm going to write a p equals equation. It's been dropped from rest, varies as the square root. Varies as the square root. What's my power going to be for a square root? Say it a little bit louder. Good guess, not -2. -2 would be if it was inversely proportional to the square. What power do you put on something as a square root? The square root of x is the same as x to some power. What power is that? 1/2. 1/2. So my power for a square root is going to be 1/2. So it varies as the square root of the distance traveled d. So my independent variable is d. We know that our power is 1/2. And then they're telling us here to use the square root of 2g for our constant of variation. If I saw this problem in the textbook and I looked up my answer in the back and it didn't say exactly this, I wouldn't be surprised. I'm going to guess that they might kind of try and simplify this and say that's the square root of 2g times the square root of d, and then maybe combine those two square roots together. If they said this and you wrote this, would you be confident that you guys had you had the correct answer. Both would be fine. I kind of prefer this if we're looking at power function. All right, that's all that's new today. Hey, nice. That's it. The rest is just going to be review. Any questions about power functions? Let me tell you about monomials before I forget. It's not in our guided notes, but it's in the assignment. So I'm just going to make a little corner up here and tell you about what a monomial is. You guys have heard that term before. Why do we need to know about monomials? Because we take monomials, we stitch them together with pluses and minuses, and that helps us to build bigger things like binomials and trinomials and polynomials. So some of your assignment questions are going to give you something. They're going to ask, is it a monomial? So here's the rule about monomials. They will come in the format a times x to the nth power. I'm changing the variables up a little bit. It looks a lot like a power function, but there's slightly different rules. This a, normally we call it our coefficient, but it can be any real number, just like before. So positive, negatives, fractions, rational, irrational numbers, all that fun stuff. But the rule for n is different for a monomial than it is for a power function. A monomial can only have non-negative integer values for n. Non-negative integers. Why didn't I just write positive integers? Is that the same as positive integers? There's one number that's not negative and it's not positive. 0. So is 0 allowed for a monomial? Yes. 0 is not negative and it's an integer. So 0 is allowed. But -2, no. 5/3, no. All right. Because of this, a weird example of a monomial is, for example, the number 42. Is this a monomial? Answer is yes, because it can be written as 42 times x to the 0th power. So technically it is a monomial. So any constant term is a monomial. Okay, let's go on to the old stuff. All right. So we're just going to do some analysis here. Sketch and analyze. I'll walk through this first one with you, and then I'm going to ask you guys to work on the second one on your own. Since we're talking about power functions, let's make this thing look a little bit more like a power function. So do you guys feel confident with your exponent rules? Could you rewrite that as 2 times x to some power? Go ahead and give that a shot. If you need to do it in a couple steps, that's fine. For example, some people might start by leaving the x squared alone, but changing that third root to a 1/3 power. And then how are we with our rules for powers? Do you guys know what to do with this 2 and this 1/3? Add, subtract, multiply, divide? Multiply. So this would be 2 times x to the 2 times a third is 2/3. All right, we're going to start by sketching a graph of this. I do not expect you to know what this looks like, although we should be able to make some guesses about it. Look at the original form of the function. Do you think this thing's going to end up being odd or even? If I stick a negative x in place of the x, is that negative going to stick around or is it going to go away? The negative is going to cancel out, so I think it's going to end up being even. So I can already predict that when I do graph this thing on my calculator, it should be symmetrical about the x-axis. And that's really about all I know about it. So let's grab our calculators and let's let it do the work for us. Y equals Doesn't matter which format we use. I'm going to go ahead and use this one, 2x. Since I have a fraction inside of my exponent, it's a good idea to wrap that fraction up in some parentheses. If you don't do that, your calculator is going to think you want it to do x to the second and then divide that whole thing by 3. Now, your window may be set to some weird setting because you had to zoom out on your last assignment or on the test or something. Do you guys remember how to go straight to the standard window? Yeah, so zoom 6. So I'm not even going to hit the graph button. I'm just going to go straight to zoom 6 because zoom 6 is my standard window. That'll reset my window in case it's set to some wacky values. If you ever do graph something and you're not seeing what you expect, that should be the first thing that you check. Go back to standard zoom level and see what it looks like. So it's kind of like a V, but it's sort of bent outwards a little bit, is how that looks to me. All right, let's make a sketch of this. In this class, when we say sketch, I'm talking just a quick and dirty, we don't need graph paper. It doesn't need to be 100% accurate. Looks something like that. And that should be enough for us to do our analysis. So we'll just burn through this list quickly, and then I'm going to have you guys do the next one on your own. So let's just go right through it. We'll start with domain and range. So domain would be all of the x values that appear on the graph, which I think is all of them, right? Now, you guys could write negative infinity to infinity if you like, but I'm not forcing you to do that anymore now that we're out of chapter 1. I'm just going to go with the good old double bar R. That's everything. How about the range? Look at that graph and look at the y values that appear on that graph. I say they're not all of the y values. I don't see any negative y values on my graph. Lots of positive ones. It looks like it's going to go up to infinity. Is 0 included? What do you think? Yeah? Would you be able to plug 0 into this function without causing any issues? Yeah. Yeah, so 0 would be included. So we could say 0 to infinity. Or you don't have to use interval notation anymore. You could say y is greater than or equal to 0 if you'd prefer. That would be the same thing. All right, we got domain and range. Check. Continuity. Is this a continuous graph? Are there any breaks or jumps or anything like that? Nope, it's continuous. Local extrema. Any local maxes or local mins? I see one. I see a local min right here. It's actually a global min, but we'll go ahead and call it a local min. And that occurs at 0, 0. What's another word that we could use to talk about local extrema? This is going to probably appear on the CWU exam. Turning points. There is one turning point. It's a local min at 0, 0. Okay, increasing or decreasing? I'd say it's doing a little bit of both. It's decreasing in this region here, and then it starts increasing over here. So we got a increasing and a decreasing region. You're welcome to use inequalities or interval notation. I think I'm going to stick with interval notation for this. So it's increasing from 0 to infinity, and it's decreasing from negative infinity to 0. Check, check. Oh, odd, even, and neither algebraically. Let me remind you, I warned you guys when we did this in class, and then I gave you some feedback on it on our first assignment afterwards, that I'm very picky about how you show algebraically whether something's odd or even or neither. Some folks miss like very small point values, but a lot of people ignored those instructions on the test. So just so we're clear, because it is going to come up again, okay? I need you to start by writing f of negative x. Not what f of negative x is, but I need you to actually write down f of negative x. And then I want you to tell me what f of negative x is. It is 2 times the cube root of x squared, except I left my x out, and I'm replacing it with a negative x. There should be an equal sign in between those things because that's what f of negative x is. And then we're going to keep these equal signs going. Either you can go to the right or you can go down, your choice. But we're creating a chain here. So my next link is, I'm going to rewrite this thing but simplify it. So the negative is going to disappear. And is that the same as the original? Yes, it is. Then I need you to write equals f of x. Okay, if it's an even function, your work needs to start with f of negative x and end with f of x. And in between, you need to show me what those things are. Everything needs to be joined together by an equal sign. This is more of like a proof than it is just yes or no, it's even or it's odd. So f of negative x equals f of x, that is the algebraic definition of an even function, which implies that there is symmetry about which axis? Even functions are symmetric about x-axis or y-axis? Y-axis. All right, so we took care of even and odd. We've got our symmetry here. Boundedness. Is this thing bounded above? No, I'd say those arrows are going to go through any wall that I build above the graph. How about below? Bounded below. Asymptotes. These are not leveling off towards some particular value. They are going to kind of flatten as the further they go out. They're going to keep flattening, but they're never going to become flat. They're always going to keep growing forever and ever. So there are no asymptotes on this one. Boundedness, asymptotes. All we have left now is end behavior. Let me remind you what that looked like. That was not on our last test, but it will be in our next one. We're going to use limit notation like we did in class. The limit as x approaches something of f of x equals, and the limit as x approaches something else of f of x equals. This graph is going to have end behavior on both sides because we got arrows going off to the left and to the right. So we need two expressions for end behavior. I'm going to do my left first. If I'm going to the left, x would go to negative infinity. And on the left side of this graph, I'm seeing the graph rise up towards a y value of positive infinity. And then I'll look at the right. If I'm going to the right, then y is going towards positive infinity. And I can see on the right side of this graph that it's also increasing up towards positive infinity. And I think that's everything on my list. You know what I didn't include on here, though, is intercepts. Let's throw that in just for good measure. You do not have to tell me if something is an x-intercept or a y-intercept. You can just say it's an intercept. I'll know if it's an x-intercept or a y-intercept because you're going to put it in as an ordered pair, and if it's got a 0 in there someplace, it's an x-intercept or a y-intercept. I'd say this one only has one intercept. That is an x-intercept and a y-intercept. 0, 0. All right, do you guys remember doing all this stuff? Isn't this fun? I love analyzing functions. If you do too, I've got great news for you. We're going to do a whole bunch of it this year. It's going to be so great. You'll love it. All right, let's do this again for the second one. It's currently not written as a power function. We don't have to write it as a power function just to analyze it, but let's go ahead and practice rewriting this thing as a power function. If I wanted to write it as a power function, it would be 2 times x to the power of what? -2. All right. If you don't know what the graph of that thing looks like right now, that's fine. Now, in about 2 weeks, you'll be able to sketch the graph of this thing super accurately without looking at a calculator, but I don't expect you to be there yet. So feel free to put that into your calculator and have a look at what the graph looks like. Make a sketch of it. And then I'm going to ask you guys to go through and do the analysis part on your own. I'll walk around, see if anybody has any questions or needs any assistance. We'll come back together in about 3 or 4 minutes. A couple of interesting questions came up as I was circulating, just as you're finishing up here. When we're talking increasing, decreasing, constant, this graph does kind of look like it gets constant somewhere along here, but does it ever truly flatten out? It's always heading down. It's never gonna, I don't think it ever actually gets to 0. We'll talk about that in a minute. That was the second question. But it's never constant anywhere. So even though it looks like it's flat over here, it is actually increasing all the way from -infinity to 0 and decreasing from 0 to infinity. The other thing that I wanted to talk about, as far as the domain goes, you're welcome to say it's -infinity to 0 and 0 to infinity. I'm also okay with you just writing all real numbers except 0. You'll see a lot of domains that are going to look like this, especially when we get into rational functions. And it'll be way easier to just write all real numbers except 0, 3, and -5 than to write -infinity to -5 and -5 to 0 and 0 to 3 and 3 to infinity. My other question was about the range. We can clearly see that this graph is going up to +infinity and it starts at 0. The question is 0 included or no in the range? And to answer that, one way we could answer that is to go back and look at the function and ask yourself, remember, the range is the y value, so what this is equal to. Is there any way I can put in a number for x and get the function to equal 0? Can you take 2 and divide it by something and get an answer of 0? Ever? No. You can't divide 2 by something and get 0. So 0 is not included because there's no way we can get a y value of 0 out of this equation. I'll put the rest of my analysis piece up here for you to have a look at and see if we have any questions there, and then we'll move on to our last example. Getting really close, guys. This one does have 2 asymptotes. There's a horizontal and a vertical asymptote. You may have gotten used to last year writing HA, y equals 0, and VA, x equals 0. You don't have to do that for my class. Write me an equation, y equals some number, x equals some number. I'll know whether it's horizontal or vertical depending on how you write the equation. We're going to get into a lot of work with asymptotes. I've warned you about this before, but I just want to remind you. If we're taking a test and you write VA 0, that is going to get you no points. Okay, the vertical asymptote is not 0. The vertical asymptote is a line. It's x equals 0. Okay, so when you're writing your asymptotes, don't write something like HA is 0, right? Y equals 0. Okay, any questions before we get into our last example? Last example is we're just going to do some tables and some transformations. Let's do it, guys. You're doing awesome. Let's wrap this up. We're going to transform this. Now, these are the exact instructions that you'll see in your assignment. I copied and pasted these in here because the first time I ran into these, I was having a hard time understanding what they were asking me to do. So it's described how to obtain a graph. That's code for we're going to do transformations. Describe how to obtain the graph from the graph g of x equals x to the n power with the same power n. So they're telling us what our parent graph is. Our parent graph is just x to whatever power it is here. So when we do this, we're going to start off with our parent graph y equals x to the 6th, because that's the power that's in the problem. So state whether it's even or odd, sketch a graph by hand, support with a grapher. On these, you only have a couple of them, and I'd like you to practice what we were doing with our transformations before. So we're going to plot some points. This is the first time we've ever done a power to the 6th power. But just use the same x coordinates that we use for all of our other graphs when we're doing transformations, -1, 0, and 1. And I trust that you guys are capable of plugging those numbers into y equals x to the 6th and coming up with y values. What's -1 going to turn into when I take it to the 6th power? Just +1. 0 to the 6th is 0. +1 to the 6th is also 1. So they're the same parent points as we've seen for one of our other parent functions. Which one? Y equals x squared, the parabola. Actually, same parent points we had for absolute value too. Our graph is going to look a little bit different from parabola, but we'll talk about that in just a minute. So let's do a transformation. We've only got 2 to do here. What do you guys want to do first? It looks like there's a reflection and a stretch or a shrink. Which one first? No wrong answer here, because we don't have any shifts to worry about. Reflection first? All right, so let's throw a minus out in front of this thing. Now it's negative x to the 6th. And that is a reflection over x-axis or y-axis. I always have to stop and think about this. It's happened on the outside, which means points would be moving vertically. If I move a point vertically, it looks like it's moving over the x-axis. And we'll go ahead and plot our points. If something's happening vertically, that should be affecting x coordinates or y coordinates. I think that's y coordinates. We're going to just multiply each of our y coordinates times -1. So those all change, but the x's stay the same. And one more transformation here. We need to get that 2 in there. So multiplying the entire function by 2. Describe that for me in words. Horizontal or vertical if we're multiplying the whole function? Vertical, and is that a stretch or a shrink? Vertical stretch by 2, good. And once again, that's vertical, so that should be affecting our y coordinates yet again. X coordinates will stay the same. And these are just going to multiply times 2. We'll go ahead and plot our points, and then before you connect them, I want to talk about the difference between this and x squared. This gives us a chance to preview something that's going to come up when we start talking about polynomials in a couple lessons. All right, you guys ready? You don't need to write this down, just see it now. It's going to pop up in our notes later on in the packet anyways. I want to show you the difference between y equals x squared, y equals x to the 4th, y equals x to the 6th, and let's just also graph y equals x to the 100th for fun. Okay, so y equals x squared, you guys are familiar with this graph looks like. It's a parabola. It's got that nice U shape to it. As we start increasing the exponent, but we keep it even, it's always going to stay in that same shape if it's even. But what's going to happen is the exponent rises, it's going to start flattening out at the bottom here. So y equals x to the 4th is going to kind of be a little bit flatter, a little less pointy. Y equals x to the 6th is going to be even flatter still. It'll kind of be like that. If you were to graph y equals x to the 100th on your graph, it's almost going to look like a right angle down here. It's going to be like a really sharp corner down there. So that's what changes when you increase the power. And we'll see that same thing happen with odd powers too. Y equals x to the 3rd looks like this. Y equals x to the 5th is going to start looking more like this. So that's going to come up again. So as we draw this, we're going to draw something that looks like a parabola, but a little bit flatter than we're used to. It's still going to go through all those points. And we'll call that good. It says to state whether it's odd or even. It doesn't say to prove it algebraically, so we can just say odd or even based on the symmetry. What do you think? Even because it's symmetric about the y-axis. All right, you guys did awesome. If you've got questions, I will be available.